All right, so welcome back. So we'll sort of talk through the answers from this little exploration. And so again, this is the series that we are dealing with here. And so the first thing said, just sort of get a handle on it, start plugging in numbers and listing out the first few terms. So we have, if I can get this lined up here, so 1 over 1 times 2, 1 over 2 times 3, 1 over 3 times 4, and so forth. And so be interesting to hear what your thoughts were on this. Of course, we're adding up infinitely many things, and so they're all positive. And so one instinct perhaps would be, oh, this has to diverge, right? If you add up infinitely many positive things, you should get an infinite answer. Sort of seems to make sense, but we know some weird things can happen with infinity. We saw this with the improper integrals from the last unit. So let's explore it a little further. And so the way we're going to explore it is, instead of doing the whole thing, doing infinitely many, we're just going to stop along the way. And so S sub 1 is the sum of the first term. That's just 1/2. S sub 2 is the sum of the first two terms, and so that's 1/2 plus 1/6. And you can even, do this by hand, get a common denominator, 4/6, which reduces to 2/3. S sub 3, of course, is just the 2/3, the thing I had before, and then add the next term, which is 1/12. And so S sub 3 is 3/4. And then S sub 4 is what I had before plus the next term. And when I do all the math and reduce the fraction, I get 4/5. And then one more, 5/6, right? And so as you do this, you start to notice a pattern. It's maybe not a proof, but we certainly start to see a pattern here. These answers are all fractions, and the numerator is 1 less than the denominator. And in fact, the numerator is the same as the term number I stopped on. So the fifth term is the sum of the first 5 terms is 5/6. And so it would make sense that maybe the sum of the first 10 terms would be 10/11. The sum of the first 100 terms would be 100 over 101, and so forth. And so it seems like potentially the formula for the sum of the first n terms is n over n plus 1. And that intuition, that pattern, turns out to be correct. And so we will confirm that in just a minute, but it is correct. Let's just make use of it now, though. The question is, what happens as n approaches infinity, right? So what happens to the limit of S sub n as n approaches infinity? Well, that means what happens to this as n gets big. And we have done problems like this lots of times before. They're both degree 1, lead coefficient is 1, and so the limit is 1. So what does this tell me about all this? We've done a lot of work now, so let's sort of zoom back out and look at all this work. Think about where this came from. So this S sub n down here, that's the partial sums of this series that I started with. And so I can add up the first term, the second term, the third term, right? All those first however many terms. And what it turns out is, as I take the limit of that, this partial sums are approaching 1. But that's just another way of saying this series is approaching 1. And because that's what the S sub n's are telling me, is what I get when I add up the first n terms. And it turns out when I add up infinitely many terms, I actually get 1. And so this is another one of those things, sort of like the improper integrals, sort of surprising, adding up infinitely many positive things. And we are not getting an infinite answer. In fact, nowhere close to infinity. We are just getting 1. So those are sort of the big ideas, and we'll see these ideas coming up again and again, and we're going to try and figure out what series converge to. If we can't, we want to at least know whether they converge and diverge. Again, just sort of like improper integrals. As just a little sidelight, you don't really need to worry about this much, but it's sort of fun to see. You can actually prove everything that we just did by using our old friend, partial fractions. So we can take this series formula, we can break it up into a over k and b over k plus 1. I didn't write it out, but I went through the work and I figured out a and b. A is 1 and b is -1. And so my series can actually be rewritten like this, right? So I just broke up the original series into its partial fractions. Notice what happens, and this trick you will see occasionally, and when you see it, it's sort of nice and it's sort of amazing. So now I've got a formula for S sub n. It's the sum of the first n terms. So again, I just plugged in 1, got this, plugged in 2, plugged in 3, and so forth until I plugged in n. And this type of series is called telescoping, and it sort of goes back to those old telescopes you'd see in pirate movies that sort of expand and collapse, right? And so we've got this telescope that's sort of extended. It's written out in a real long way, but we're going to collapse it now by just noticing that, oh, I've got a -1/2 and a +1/2. Oh, I've got a -1/3 and a +1/3. Oh, I've got a -1/4 and a +1/4. And that continues all the way along. Everything has a partner except the very first thing and the very last thing. So S sub n, after all that work, is simply 1 minus 1 over n plus 1. If I just get a common denominator and simplify, I'm back to the exact same thing I had gotten on the other side. S sub n equals n over n plus 1. So it's just a nice little proof of the pattern that we saw first. And it also shows you an example of a telescoping series. And like I said, when that pattern comes up, when you just write out the first few terms, you sort of notice it and you get what you need. Hopefully you had some fun with that. You should have some time, hopefully now, to work on a bit of homework. And we'll see you in a couple days.